Hey there, and welcome to The Explainer. Today, we're going to talk about something that's literally all around you, hiding in plain sight. I'm talking about the chemistry behind the antiseptic in your first aid kit, the shiny finish on your coffee table, even the perfume you might be wearing. So let's just jump right in with the puzzle. What could things like wood polish, perfume, and even paper possibly have in common? I mean, they seem totally different, right? But believe it or not, they all share one secret ingredient.
And that secret ingredient, it's a single, super powerful atom, oxygen. But it's not just that it's oxygen, it's how this one atom decides to bond with carbon and hydrogen. That's the key that unlocks three totally distinct and super useful families of organic compounds.
All right, so let's pull back the curtain and meet these families. We're going to get to know the alcohols, the phenols, and the ethers. And it all comes down to how they use that oxygen atom.
Okay, first up, the one you've probably heard of, the alcohols. So what makes an alcohol an alcohol? Well, you take a simple chain of carbons and hydrogens, and you just swap out one of those hydrogen atoms for an OH group. That's it. That little OH group is the signature of the alcohol family. Next up, we've got the phenols. I like to think of them as the alcohol's more sophisticated cousins. You've got that same OH group, but here's the twist. Instead of being attached to a simple chain, it's hooked directly onto a super stable circular structure, an aromatic ring. And trust me, that one little change in real estate, it gives the molecule a completely different personality and changes everything about how it behaves.
And then we have our third family, the ethers, which kind of rewrites the rules. See, instead of having that OH group hanging off the end, an ether has an oxygen atom playing matchmaker. It acts as a bridge, linking two different carbon groups together. So the oxygen is right there in the middle of the action. It's a really unique setup, and it's what made diethyl ether famous as an early and, yeah, pretty flammable anesthetic.
So if you take away one thing from this part, it's this. It's all about location, location, location. Is that oxygen part of an OH group on a chain? Is it on a ring? Or is it playing the role of a bridge? That one single difference, it defines everything about which family it belongs to. All right, to really understand these guys, we've got to learn to speak their language, right? And that means digging into how chemists actually classify them based on the nitty-gritty details of their structure. So it turns out, even inside the alcohol family, there are cliques. It all comes down to the specific carbon atom that's holding on to that OH group. You have to ask, how many other carbons is that carbon attached to? If it's just one, we call it a primary alcohol. If it's two, it's secondary. And if it's holding on to three other carbons, you guessed it, it's tertiary. And listen, this sounds like a tiny detail, but it completely changes how they react. It's a huge deal. You know what's really cool is how logical the official naming system is. It's actually super straightforward. You just find the longest carbon chain, take its name, say ethane, and then you just swap the E at the end for all. Boom, ethane becomes ethanol. It's pretty elegant, right?
Okay, so we know who they are, we know how to name them, but how are they made? Where do they come from? Let's take a look at one of the most common origin stories for an alcohol.
So a really common way to do this is something called acid-catalyzed hydration. And really, it's like a little three-step chemical dance. Step 1, an acid gives a proton to an alkene, that's a molecule with a double bond, which creates this unstable positively charged thing called a carbocation. Step 2, a water molecule sees that positive charge and bam, it attacks. And finally, step 3, the whole thing just wants to be stable, so it kicks off a proton to balance things out. And there you have it. You've just made an alcohol.
Now for phenols, the process on an industrial scale is a bit different. The way most of the world's phenols is made actually starts with this hydrocarbon called cumene. And what happens next is pretty clever, actually. Through a couple of steps, chemists are able to split the cumene molecule into two really valuable things at once. You get the phenol you wanted, plus you get acetone. Yep, the same stuff in nail polish remover. It's a super efficient process.
Okay, so we've seen how they're built. Now let's get to the really interesting part, their personalities. How do they actually behave? Because the way these molecules are put together has a direct impact on how they act in the real world. And we can start with something as simple as boiling point. This chart right here, it basically shows you the superpower of alcohols. Just look at ethanol. Its boiling point is way higher than a similar-sized ether or hydrocarbon. And you gotta ask, why is that? Well, it's all because of that OH group. It lets alcohol molecules form these really strong connections with each other called hydrogen bonds. It's kind of like they're all holding hands in a big group. And that makes it a lot harder to pull them apart and boil them into a gas.
Ethers just can't do that because their oxygen is stuck in the middle. But okay, if you want to see where their personalities really split, we have to talk about acidity. Get this, phenol is about a million times more acidic than ethanol. A million. That is just a staggering difference. I mean, they both have that OH group, so what in the world is going on?
The secret? It all comes down to stability. See, when an alcohol gives up its proton, that leftover negative charge is just kind of stuck, stranded on the oxygen atom. But when a phenol loses its proton, something magical happens. That negative charge gets to go on a tour. It spreads out over the entire aromatic ring. It's like sharing a heavy load among a bunch of friends. This sharing of the burden makes the whole thing, which we call a phenoxide ion, incredibly stable. And because it's so stable, it's way more likely to happen in the first place. That powerful acidity is precisely why phenol was one of the first major antiseptics. Okay, enough with the theory. Let's make this real. Let's meet the two most famous members of the alcohol family, methanol and ethanol. You can think of them as chemical siblings. They're almost identical, separated by just a single carbon atom.
Now on paper, they're both fantastic solvents, super useful in industry. But when it comes to the human body, well, it's like a classic story of the good twin and the evil twin. Ethanol, that's the spirit in alcoholic drinks. But methanol, sometimes called wood spirit, is a deadly poison. We're talking a tiny amount can cause blindness or even death.
So what makes it so incredibly toxic? Well, the crazy thing is, it's not the methanol itself that's the real villain. It's what our own bodies turn it into. When methanol gets to your liver, your enzymes get to work on it, and they metabolize it first into formaldehyde. Yeah, you heard me right, embalming fluid. And it doesn't stop there. That's then turned into methanoic acid. And that acid is what causes all the catastrophic damage, the blindness, the organ failure, and death.
And this is where the story takes a truly incredible plot twist. The antidote for methanol poisoning is its own sibling, ethanol. Isn't that wild? It turns out the very same enzymes in your liver go to work on both alcohols. So by giving a patient a carefully controlled IV drip of ethanol, doctors can basically create a distraction. The enzymes get so busy working on the ethanol that they don't have time to touch the methanol. It's a brilliant chemical trick that buys the body enough time to flush the dangerous methanol out before it ever gets turned into that deadly acid.
And that really just leaves us with one final, kind of mind-bending thought. How can one tiny carbon atom be the only thing separating a deadly poison from its own antidote? It's just such a powerful reminder that in the world of chemistry, the absolute smallest changes can have the most massive consequences. It really blurs that line between something that can heal us and something that can harm us.